I'm doing this video especially on conventions used in optics because when we discuss spherical mirrors and spherical lenses, we use them frequently. And we'll just quickly go through the conventions used so that whenever we're discussing any particular topic, you'll be able to get an idea about how we are deriving or how we are arriving at a particular equation or a concept based on these conventions. So a brief short video on various conventions used. The first convention that is used in optics or spherical mirror is U and V, that is the distance of the object and distance of the image. So we will use the symbol U for distance of the object and V for distance of the image. So this is for distance of the object and this is for distance of the image. So if I take let us say a mirror, we know this is the pole of the mirror. Let us say this is the object image over here, and let us say the image is over here. I'm just taking random cases, right? So OP represents distance of the object. So this distance is U and this distance is V. Yes, as far as the convention is concerned, the convention that we'll use is if PO, that is we start from P and go in the direction of the object, and if this direction is same as the direction of the ray of incidence, then we'll take it positive. Let me repeat. If the direction from P to the object or from P to the image, if it is same as the direction of the incident ray, then we'll take it as positive. If it is opposite to that, then in that case we'll take it negative. So in this case, for example, this is the object, so a ray will go and be incident like this. Now this is the direction of the incident ray, as you can see, that ray is going from here to here. This is the direction of the incident ray. What is the direction of the distance of object? We have to start from P and go towards the object. So we're going in this direction. So in this case, I will have U with a minus sign because it is negative. What about distance of image? I have to start from P and go towards I. So I'm going in this direction. And as I can see, these directions are same. So I will have minus plus V. So this is the convention we'll use. So we have to look at the direction of the incident ray and compare it with the direction of the distance of image or the distance of the object. Remember, we have to start from P. This is the convention we will use for distance of object and distance of image. Same convention, similar convention we will use for height of object, which we can call as HO, and height of image, which is called as L. Now, this is, say for example, the object, this is AB, and let us say this is the image, which is A dash, B dash. If the height of the object is above the principal axis, this is the principal, if it is above, then we will assign it positive sign. And if it is below the incident, we will assign it negative sign. In other words, if the object is, or if the object is erect, or if the image is erect, then positive. If it is inverted, it will be negative. Of course, the height of the object, HO, will always be positive because we're never going to keep an object inverted. So the object, this HO will always be positive. HI, if it is erect, positive. If it is inverted, negative. So this is the second convention we will use for height of the object and height of the image. So in this case, it is with reference to the principal axis, whereas here it is along the principal axis. Okay. Third convention we'll use is, or assumptions we'll make is, the aperture of the lens or the mirror is very small. Right? So let me take the example of, let us say, a convex lens. So let us say this is the convex lens. And we will assume that the aperture is very, very small. Just for sake of diagram, we show them big like this, but actual lenses would be small, and therefore the aperture is small. And if the aperture is small, if this is, say, P, if this is the point of incidence, say a ray of light is starting from an object and going over here. We drop a perpendicular M over here. Let us say this is M. If the aperture is small, if this distance is very, very small, then I can say that PO is equal to MO. Because this distance will be extremely, extremely small. So I can assume that PO is equal to MO. that's based on the assumption that the aperture is small. So if I actually show you, if I show a very small aperture, let us say I show you a very, very small aperture, and then I drop a perpendicular. As you can see, this distance will be extremely, extremely small, and therefore we can ignore this distance, this one, and therefore PO is equal to MO. So that's an assumption we'll make. I will always assume aperture to be small, and then we will take these, we'll ignore this distance PM. We will always take PO equal to PM. So that's a convention or assumption 3. Fourth, generally the angles that we come across, say for example, the angle of incidence in this case, so this would be the normal and this would be angle of incidence. The angles will be very small. That's an assumption we are making, and because this mirror, the lenses or mirrors are extremely small in size, the angles would also be very, very small. And if the angles are very, very small, then we take sine theta is equal to tan theta is equal to theta, right? Where theta is of course the relevant angle, angle of incidence or angle of refraction or any other angle. We'll take these as equal. And the reason why we do this is because if we actually try to see what is sine theta and tan theta, let me take a bigger angle. Let us say this is angle, it is called this A, B and C. Then we know that sine theta is equal to opposite side upon hypotenuse AC. This is B. Tan theta is equal to opposite side AB upon adjacent side BC. Now, if I take an extremely, extremely small angle, then this diagram will become something like this. This is theta, this is C, this is B, and this is A. Now, what is sine theta? Sine theta is AB upon AC, AB upon AC. Tan theta is AB upon BC. As you can very clearly see over here, since this angle is extremely small, BC and AC will be equal. I can take BC equal to AC. And if BC and AC are equal, that means AB upon AC equal to AB upon BC. Numerator is same, AC and BC are equal. Therefore, we take sine theta is equal to tan theta. Both of them will be equal because these two distances, AC and BC, are equal. Finally, as far as theta is concerned, the angle is concerned, angle we know is angle is equal to arc length upon radius. Now, in this case, this arc length, so or rather, the arc length will be something like this, isn't it? Now, this arc length and this length will be equal because we are assuming aperture to be small. So, arc length will be equal to AB, and therefore this will be equal to AB. Radius is the distance from C to B, and we know BC is equal to AC, so I can again take this as either AC or BC because both these are equal, nearly equal, because this distance is extremely small. So theta also turns out to be AB upon AC, AB upon AC, AB upon AC, and therefore we take sine theta is equal to tan theta upon is equal to theta. So for extremely small angles, sine theta will be equal to theta. And therefore what will happen is, say for example we are using Snell's law. I'm short of space over here, maybe I'll use this space over here. Snell's law, we know mu is equal to sine theta, sine I upon sine R. And since I and R are extremely small, mu can also be taken equal to I upon R, which are the values which are theta. So this is another thing which we'll be regularly using when we are looking at derivations or any other aspects of optics. Right. So keep these conventions or assumptions in mind whenever we are looking at some concepts, and I will be referring to these quite often when we are looking at some derivations related to optics. Thank you.